All right, we are going to do our final section of notes for the unit and the semester, and it is about vectors. So this is a little meme. I hope you know what movie this is from. If you don't, I'm disappointed in you. So a vector, this is a quantity which we can represent visually on a graph, which is what we're going to do, but it has both direction and magnitude. So these are the two things that constitute what a vector is. So direction, that just corresponds towards where the arrow is pointing. So the direction in which the arrow points. And then the magnitude, that is just talking about the total distance of a vector. So it starts at the initial point and it ends at the terminal point. I left my Apple Pencil in my classroom, so I'm using a stylus, which is why my handwriting is a little worse than normal, so I apologize. Now, vectors have a lot of applications, and it's actually something that you explore a lot in calculus, especially calculus 3. But after geometry, in most math classes, you're really not going to touch on it much until then. So it's kind of an interesting topic that we get to discuss for a section here. So if we take a look at our first example, so there's some notation that I'll introduce to you. So if we're talking about a vector, so in this case, vector OL, I'm going to label it with this vector symbol. So it's just a line, and then it's basically like half an arrow. So it almost looks like a ray symbol, but it's only half of it. And so that's how we denote a vector. So vector OL, and we are asking in this example, what is vector OL as an ordered pair? And then we want to round the coordinates to the nearest tenth. So here's how we would approach this. We're going to use trig, and so we're going to use a lot of trig when we're dealing with vectors and we're trying to find magnitudes and representing them as ordered pairs and such. But this is our vector OL. So it starts here at the origin, so that's its initial point, and then its terminal point is right here at the end of the arrow. So this orange arrow is our vector OL. Now, we're asked to represent this vector as an ordered pair. What that essentially means is we're trying to figure out where is the terminal point, so the end point here. Because this vector, is this sort of line in this area, but we're just really interested where it ends, the terminal point. So hopefully you can tell we're able to construct a triangle here. So we have this side, the magnitude is the hypotenuse of this triangle, and it is 65 units. So we're going to use that. And so let's go ahead and just make sure we know that that represents the hypotenuse. We're dealing with a right triangle, so I'll go ahead and write that in. And then since we're focused on angle 50, that's our reference angle right in here. And so because that's our angle, then y, this side here, is my opposite side, which means x here is the adjacent side. So that is all good terminology for us. And then we can reference SOHCAHTOA. So I'm going to write that up here if this is a helpful mnemonic device for you. It is for me still. And so if I look, I have the I have the hypotenuse. And so to figure out both of these variables, I can use the hypotenuse. And so I want to make sure I'm choosing trig functions that use that. And then whichever variable I'm solving for, I'll just use the trig function that deals with that. So in this case, for x, that's the adjacent side and the hypotenuse. So adjacent and hypotenuse, that is going to be cosine. So to figure out what x is, I can start to write an equation where I take the cosine of our angle, which in this case it is 50, and this should equal the ratio of the adjacent side divided by the hypotenuse. So the adjacent side is x, and the hypotenuse we said is 65. So this is the equation that I can make that involves my variable x. And then just some simple algebra will help us solve. So if I multiply both sides by 65, I will now have x by itself. And then if I plug all of this into my calculator, 65 times the cosine of 50, you should get approximately 41.8. And they asked us to round the coordinates to the nearest tenth, so that's just one decimal. So what this tells us is the x-coordinate, because we measured this distance to be 41.8. Well, if that's this distance, then that represents the x-coordinate for this point. So I can go ahead and start my ordered pair. I know that 41.8 is the x-coordinate, so I'll write that in. And now we just need to figure out what is the y-coordinate. So we'll figure that out by finding this side length. So because now I'm dealing with the opposite and the hypotenuse, I'm going to use the trig function sine. So I'll go over here, and we will now take the sine of our reference angle, 50, and that is going to be equal to the opposite side divided by the hypotenuse. So y divided by 65. Going off the paper now. So very similar as far as how we solve. Multiply both sides of the equation by 65. Now y is by itself. And if you plug all of that into your calculator, you should find that y equals negative 49.8. Okay, so I circled these. These are not the answer, so maybe I shouldn't have circled them, but because they're asking us to find the ordered pair. That's what our answer is. So these are just the parts of the ordered pair that I need. So I'll write this in. So negative 49.8 is the y-coordinate. And so this ordered pair is my final answer. Now you might be asking yourself, well, why do we have a negative number? We're dealing with distances, right? So these should all be positive. Well, now that we're dealing with vectors, we actually have a sense of direction on a coordinate plane. And so now we can deal with negative lengths because that helps us figure out what direction we're going in. Because if x is positive, we're going to the right, and if x is negative, we're going to the left of the origin. And then similarly with y, if we would have been going upwards, then that y value would be positive. But since this vector goes to the bottom right, well, the x value will be positive, that makes sense, but our y value is going to be negative because now we're in the fourth quadrant here. So that's why we have a negative value in our ordered pair. So now we have to kind of be on our toes and look out for negative values. Okay, so that was our first example with a vector. Let's go ahead and look at another type of problem that we'll see. So we can describe the direction of a vector just using like the compass directions, so north, south, east, and west. So we can do this when given a graph. And the way we do it is relatively simple. We have to use two different directions. So in this first one here, I see that my vector is just below the east direction. So if it's below the east direction, that means it's going towards south. So the way I could talk about this vector directionally is I could say it is 25 degrees south of east. So I know this might seem kind of weird, but we can see that we're in the eastward direction, but then it's 25 degrees below it, or 25 degrees towards the southern direction. So that's why we say this vector is 25 degrees south of east. Okay, so east is the reference direction, and then south is the direction that the vector is going based on this angle. Okay, so another example, if I look at this one, you can see we're measuring the angle from the north direction, which means if we're going to the right of north, we're going towards east. So this vector is going to be 35 degrees, because that's the angle. So 35 degrees east of north. So that means I'm starting at north. So we're starting at north, and now I'm going 35 degrees east of north. So that's in the right direction from north. So if we take this to example 2, what is the direction of this vector? I want you to pause the video, think about it for about 15 seconds if you need that much time, and then unpause and see if you figured it out. Okay, so this vector is 60 degrees south of west. And that is, again, because our angle is being measured from the westward direction. So you see that this little angle measure arrow here, this blue one, it starts at west. So that's our reference direction, and we are going from west 60 degrees southward. So this vector is measuring 60 degrees south of west. So that's how we can talk about the direction. Now, if we look at our next example, example 3, this one is a little more of an application. So we have an airplane, and this airplane lands 40 kilometers west and 25 kilometers south from where it took off. So 40 kilometers west and 25 kilometers south. So let's go ahead and draw a picture. So I'll just make a graph over here. So 40 kilometers west, well, that means I'm going left as far as a graph goes. So I'm not going to make a bunch of tick marks. I'm just going to say this distance here would be 40. And since I'm going left, then on a graph, that means it's actually negative 40. So I'm going to label it that way because we're going to be talking about coordinates. And then 25 kilometers south, well, that's just going to be 25 down. And again, that is in a negative direction. That's where our y value would be negative. So this is negative 25. And so the next part of the problem says this trip can be described by the vector negative 40, negative 25. And something that was not included as a part of notation, when we label a vector as a coordinate like this, we need to include these little triangle parentheses. Okay, so they're just kind of like two little arrows that border the numbers. So the vector negative 40, negative 25, well, that's just going to be the vector that has a terminal point at negative 40, negative 25. So that vector looks like that little blue line. So this is the ordered pair here, negative 40, negative 25. And so we're just showing that this blue vector has the ordered pair here as its terminal point, and this vector is modeling this airplane's path. So this airplane took off and it landed 40 kilometers west and 25 kilometers south. So we are asked to figure out the approximate magnitude and direction of its flight vector. So the two things we need to figure out are the distance of this vector from the origin to this point. So we need to figure out how long is this line. And then we need to figure out its direction. So we need to figure out this angle measure in here, and then we need to describe it similarly to these problems up here. Okay, so two different things we have to do. The first thing we want to do is figure out the magnitude. So the way we can do that is actually through the Pythagorean theorem. So I can make a triangle here. I'm going to use some dashed lines. So we'll make this our right angle. Now, I should know what this distance up here is because I already know when this leg of the triangle ends. It ends at negative 40. So the positive distance of that segment is just going to be 40. And then in a very similar way, I should know the distance measured on this leg of the triangle. It should be 25 because this distance ends at negative 25. So if I think about this triangle, I know that this leg is 40. I know that this leg should be equivalent to this spot over here, which is 25. So maybe I'll label it over here. And so I have a right triangle, and I have both the legs, and I'm trying to find the magnitude, which in this case is c. So I can simply use the Pythagorean theorem of a squared plus b squared equals c squared, where I'll say a squared, well, I'm going to make that 25 squared, and b squared, I'll make that 40 squared. And we need to figure out what is c squared. After doing a little bit of work, you should realize or come to the conclusion that c equals 47. So I'm not going to show all the work, but I trust that you're smart enough and you're able to do that. And then our label is kilometers because that's the unit that we're working in. So this is the answer for the magnitude of this vector. So we're halfway there. Now we have its magnitude, but now we want to figure out what's the direction of this vector. How do I know how much this angle here is? Maybe I'll call it angle x. And there's a few ways we can do this, obviously using trig. So I can take a certain trig function of this angle because I know all three side lengths. So I can set a trig function equal to its respective ratio, and we can solve for our variable that way. So I'm just going to take the sine of angle x. So I'll write this down here. So if I take this sine of angle x, well, the sine, if I think of SOHCAHTOA, that's going to be taking the ratio of the opposite and the hypotenuse. So in this case, our opposite is 25, and the hypotenuse, the magnitude we just figured out, is 47. So if I want to solve for x, I need to take the inverse sine of both sides. And so if I do that, then x is going to equal the inverse sine of 25 divided by 47. And then plugging this into my calculator, I should figure out that x equals 32 degrees. Okay, but that's not quite our answer because we still need to describe this vector directionally, because it's 32 degrees, but it's specifically in this fourth quadrant, and we measured from the x-axis to the vector. So if I want to describe this vector directionally, I can say that x, the angle, is 32 degrees, and if I really pay attention, we measured from the x-axis to the vector. So I started in the westward direction, and we measured towards south, and we measured south exactly 32 degrees. So I could say that this vector is 32 degrees south of west, because we started in the west direction and then we went 32 degrees southward. So that is our answer for direction, and then we already found our answer for magnitude. So that is it for example 3. I know that was quite a bit of work, but hopefully that makes some sense for you guys. Okay, and then this leads us to the last part of the section, which is how we add vectors. So again, just some notation that we want to label out. So we're talking about two vectors, vector A and vector C. And I'm using x and y to represent the numbers within the coordinates of these vectors. So I'll use the arrow parentheses. So if I want to add two vectors, A and C, so vector A plus vector C, we can compute that by doing this. We're going to take both of the x values, so I'll do some highlighting here. So my x values are red, and our new x value from adding these two vectors is just adding both x values. And then in a similar way, to find the y value of this new vector, I'm going to add up both of the y values from the previous two vectors. Okay. Now, when you add two vectors together, the result is called the resultant. So if we go down here, vectors A and C are shown in the graph. So I have the two vectors here in this graph. So here's vector A, here's vector C. And we're asked, what is the resultant, which we are labeling as vector E, of the two vectors as an ordered pair? And then they also want us to draw vector E. So first we have to figure out what is vector E if I add these two vectors together, and then how could I draw it on the graph? So we are trying to figure out what vector, so vector E is equal to vector A plus vector C. And we want to figure out what that is. Well, to do that, first let's go ahead and define vector A and vector C as ordered pairs here. So vector A, if I take a look, it goes from the origin to this point, which is at -4, -3. Okay, so I'm just figuring that out by measuring -4 to the left and -3 down, and that will meet at the terminal point of my vector. So vector A is -4, -3. And then vector c over here is going to be when x is 1 and when y is -2. So vector c is the vector 1, -2. Okay, so these are the two vectors that I'm adding together to get vector e. So let's go ahead and write this down. So vector e equals vector a plus vector c. Well, that's going to be vector -4, -3, because that's vector a, plus vector 1, -2. That is vector c. Okay, so now that I have those, I can simplify this a little further and say, well, actually, what I'm going to do is I'm going to take the two x values, so in this case, -4 and 1, and I'm going to add those together. So I'll take oops, that's my highlighter. So I'm going to take -4 plus 1. That's my new x value. And then I'm going to take -3 and -2. I'm going to add those together. So -3, you could either do plus -2 or just -2. And that'll be my new y value. So I'm just taking the x values, adding them together for my new x value. And then I'm taking the y values and adding them together for my new y value. So if we go ahead and simplify this or solve it, I ran out of space again, so I'm going to write, I'll just go over here. So my new x value, -4 plus 1, that is just -3. And my new y value, -3 minus 2, is -5. So this is the representation of our resultant vector e as an ordered pair. Now, to graph this, it's pretty simple. We just graph this point, -3, -5, and then we'll draw the vector that has that as a terminal point. So -3, -5, if I look here, that is 3 to the left and 5 down, so that point is right there. So -3, -5, and then I'll go ahead and draw a vector from the origin to that point. That is not the best line I've ever drawn, but you can kind of see that this is where these two vectors would meet. If I combine their directions along with their magnitudes, this is the resultant vector that we would get. Okay, so it's pretty cool that we can get an accurate graph just by doing some very simple math. Okay, final example. We have two vectors. I'm going to get the labels in here. So vector 2, 3, and vector -4, -2. And we are asked, what is the resultant of these two vectors as an ordered pair? So I might assign a variable, so I'll just say that vector r, this is going to represent the resultant. And now, if I want to figure this out, vector r is just going to equal the sum of these two vectors. So I'll take vector 2, 3 plus vector -4, -2. And so, adding these together, I add the x values, so 2 minus 4, or 2 plus -4, and then the y values, 3 minus 2. Okay, so once again, I'm just taking both x values, adding them together for my new x value, and then I'm taking both y values and adding them both together to find my new y value. Doing this, I get the new vector, our resultant, to be -2, 1. And that would be our final answer. And that concludes this section of notes.